Thank you for being here. I'm going to take just a moment by way of introduction, and then we're going to get into our lesson class. You are my class tonight, and this is a little different than a normal meeting type arrangement, but the elders have approved our dealing with this as a science lecture. So I hope you're ready, and I have a few ground rules in my class. I expect rapt attention, and I do not allow sleeping, and I can see you. I've been teaching for a long, long time, and you cannot hide. So if there is somebody that's getting drowsy, which probably I would if I were sitting your place, we'll do something about that. But welcome. Glad you're here. You live, class, in one of the most exciting times in the history of mankind with regard to this topic, our topic tonight. We're going to be talking about the chemistry of living things. And we have learned more about that in the last 75 years than in all of the time in human history before that. It's an exciting time. And science has produced this information for us. Examples. In the 1950s, many amazing things opened up for us. James Watson and Francis Crick were given credit for discovering the structure of DNA during the 1950s, for which they received the prize. Also in that century, Friedrich Sanger, which you've probably never heard of, sequenced the first protein. Never happened in the history of mankind prior to that. He received the prize for that also. This man, Friedrich Sanger, is one of, I think, maybe two people that got 2 Nobel Prizes in chemistry in his lifetime, because he also sequenced DNA the next decade. So all of that's happened since the 1950s. There was something else that happened in the 1950s that changed our lives. I've written down the date because I can't ever remember it. It's October the 4th, 1957. Now, some of you are old enough to be alive then, so help me. By the way, this is my class, so you can answer my questions. What happened on October the 4th, 1957 that shook up the whole world? Say it again. Sputnik. Thank you. That's exactly right. And young people, do you know what Sputnik is? Okay. It was the first space object put up in space, and everybody knew they were going to take over the universe if they ruled from space. So there was a great movement in the United States to increase science education and make us catch up with the Russians. And if I may be a little bit personal here, I got a personal benefit out of that, because our Congress sent a bunch of money out to the colleges, and especially Harvard University, and Harvard chose to take their money and give 50 scholarships to science educators to come and earn a master's degree. Full rides. I got the full ride for Florida. They gave one to every state. And I got the full ride from Florida to go to Harvard. Had no intention of going there. But it was an open door, because what we were going to do is rewrite the curricula for high schools and colleges to increase our education. I had a part in rewriting the Chem Study Chemistry curriculum. Anybody in this class ever take Chem Study Chemistry? Okay, good. Thank you. You have to be old to have taken that. But it was a great revision of our whole science education program. I'm saying all that to you, class, to say you've lived in an exciting time with regard to the unfolding of information about chemistry of living things. And because of that, what I'm going to talk to you about tonight, in my mind, has opened one of the greatest doors by God Himself to testify who He is. But that's not the way it was taken. I want to share with you some specifics. This is a piece from the Humanist Manifesto, number 2, in 1973. We find insufficient evidence for the belief in the existence of a supernatural. This was signed by, my memory is 50 some odd people, scientists, intelligent people who were of the humanist persuasion. It is either meaningless or irrelevant to the question of survival and fulfillment of the human race. As non-theists, we begin with humans, not God. Nature, not deity. Nature may indeed be broader and deeper than we now know. And any new discoveries, however, will but enlarge our knowledge of the natural. You listening to me, class? The humanist doctrine is nature's all there is. There is no evidence for anything beyond it. A little later in that same document, we can discover no divine purpose or providence for the human species. While there is much that we do not know, humans are responsible for what we are or will become. No deity will save us. We must save ourselves. And so the whole doctrine of humanism was humans are the important thing. Well, what you need to know, class, is that this was a very strong thing being taught in the 1960s. When I was going to college, I went to Harvard in 1967. This came out in April the 8th, 1966, Time magazine. Is God dead? And the reason it did, ladies and gentlemen, is because that was the movement of the time. And I had him sing the first and the third verse of that song, you noticed. The third verse says, secure is life from mortal mind. God holds the germ within his hand. Though men may search, they cannot find, for God alone does understand. I had him sing that because we had a professor at Florida College, where I was a teacher for many years, who refused to sing that verse because he didn't believe it was right. He was a Christian, taught biology at our school, but he wouldn't sing that verse because that gentleman believed within a relatively short period of time we would have learned how life came about and how to make it, and that we didn't need God for life. That's scary. But the movement that was taking place in that time, based on all the amazing discoveries we were making about life at the biochemical level, led men to be very heady about their knowledge versus was there God. So this movement very much represented what was going on. And you may not know, but quoted in this book, well, first let me tell you, A.W. Dicus wrote that song that we just sang. He was the academic dean at Florida College. So I literally sat in his seat. He was also a physicist, widely respected, and he wrote this song specifically to answer that. You can see the dates. And I love it when congregations sing loudly and clearly, "Our God is alive. In him we survive and we live." Our God is not dead. But Thomas J.J. Altizer and William Hamilton, in their book Radical Theology and the Death of God, who are quoted in this Time article, said things like this: we must realize that the death of God is an historical event, that God has died in our cosmos, in our history. Ladies and gentlemen, those men are theologians of the, quote, Christian religion. And they went on to say the dead God is the God of the historic Christian church. and beyond the church of Christendom at large. So here are two preachers teaching that God has died in our generation. That was the movement. And may I say to you, I suffered from that as a student at public universities, because professors, numerous of them, were of this ilk, and were saying to students, if you're a believer in God, you best get over it, because we are learning so much more about the way nature works, and everything we learn removes that another piece of what you need to believe in God. The more we learn, the less we need God, was the notion. And as a result, a host of young people became unbelievers. And in our time, a little bit down the line, atheists became evangelistic. And they're pushing this in some cases, ugly ways. So it is a time, ladies and gentlemen, in my judgment, when what I'm doing tonight is critically needed. And I thank the elders for providing such an opportunity. I thank you for being here. If you're here tonight and you're not a believer, or if you're a believer who's having doubts about his confidence in the existence of God, or if you're an agnostic in terms of your views, thank you for coming. Because it says you're at least willing to listen. There's another side to this story. I like this book better. Is Atheism Dead? Now, this one wasn't written by a scientist. Eric Metaxas is not a scientist, but he's a well-read gentleman, and he's done his homework on this. So, in this book, he starts this way. Since the Time article in 1966, which I just showed you, roughly 5 things have arisen to challenge, and I will argue to overturn the secular consensus formed in the wake of that article. And he said it just right, class. The secular consensus that followed, because that's exactly what happened. And he claims there are at least 5 things that have happened that he believes will overturn. I hope so too, because I want to be a part of it. And here are his 5 things. He says, science has demonstrated there's a beginning. We talked about that last night, didn't we, class? Do something with your head. Those of you that were here, you do remember that, right? No, yeah. We're not going to talk about that in detail in this series, but there is abundant evidence from science there was a beginning. That does not sit well with most atheists, because they want matter to be eternal. But the evidence is overwhelming now. That's not the case. Time, matter, and space all have a beginning. Second, fine-tuning. Did we talk about that last night, class? Just right. Yeah, I had everybody saying, just right, because we read from the Goldilocks Enigma, didn't we, by Paul Davies, who is an atheist, but clearly proclaims in that text, everywhere you look, it looks like things are just right to support life here on earth. That's the truth. And we showed you some of that last night. The third thing in his book is stupefying complexity. I told you, when you leave tomorrow night, because all of you are coming back, of course. No, I know some of you can't. But I hope you'll listen. When you get through tomorrow night, I want you to be stupefied. And what I mean by that is this: so overwhelmed with the majesty of your Creator that you'll never be the same again, because you've had a deeper appreciation for who He is. That's what this is about. And it is stupefying. And look, the only way I can stupefy you is to get enough detail in here that I'm going to lose most of you. It's okay. I want you to get the main point. And you can do that without understanding all the details. But you need some detail to be stupefied. And then he talks about archaeological discoveries. That's certainly not our topic tonight. And then fifth, he said, we have learned what atheism produces in this century. And I do want to share with you just a little bit of that information out of this text, because you have lived it. The 20th century, class, was the age of atheistic dictatorships. And it has demonstrated what they have to offer. So, it remains an unendurably horrible fact that dedicatedly atheist regimes in the last century, the 20th century, alone, tortured and murdered multiplied millions, usually for their Jewish or Christian faith. In fact, those murdered by the handful of atheist regimes amounts to about 150 million people just in the last century. And I want to make it even more graphic. In the year 1937 alone, dedicatedly atheistic Soviets, you think Hitler killed a lot of people? He didn't touch top side or bottom of what the Soviets did. In that year alone, they murdered 106,300 clergymen. They hoped they would help to eradicate the evil of the Christian religion from the face of the earth. We lived in Romania for 2 years, and we heard the stories from people there who were taught from the time they were little children that not only is religion foolishness and belief in God is stupid, but it's the opiate of the people and it's dangerous, so it must be obliterated from the face of the earth. The Soviets, in the course of their adoption of what they called scientific atheism, murdered between 12 and 20 million human beings. Many of them primarily because they were believers. What does atheism have to offer this world? A lot of horrendous things, as has been made very clear in the last century. So is atheism dead? I hope it's on the way. I would recommend that book to you. It's written so that the average person can read it well. I've done each night, and I will tomorrow as well. I've started, because we're in a church building, by quoting a scripture from the Bible that supports what I'm doing. The passage that is our theme passage is Romans 1. It says, from the creation, the invisible attributes of God can be seen. And how is that? They are seen by the things that are made. And what you can determine from that is he must be eternally powerful, and he's not part of nature. He's outside of nature. That's called the argument from design in philosophy class. That's the argument I'm going to be using tonight and tomorrow night, as we did last night. There is design everywhere. And it's very clear. Everybody admits that. The question is, what does it mean? So the Bible supports this approach. So may I say again tonight, we're not going to be using this book tonight in this lecture. I love teaching from this book. I believe it's the Word of God, and it needs to be taught above all else. But tonight, I want to turn to God's other book, the book of the natural world, in which he also speaks loudly and clearly to all of us. So, class, are you ready for a chemistry lesson?
Yes, sir.
Thank you. That was pretty good. I want to hear it again. Are you ready for a chemistry lesson?
Yes, sir.
Thank you. That's the kind of enthusiasm I expect. And there are going to be many times I ask you questions tonight, and I want a group answer. And I expect enthusiasm and alertness. And I'm going to tell you the answers. So that's so helpful. All right, here we go. Evidence from the chemistry of living things, the great design is the theme tonight. So, class, welcome to the first day of biochemistry. We're so glad to have you as a student today, and welcome to the class. I know that your goal is to attend every class period and come ready to learn and to be attentive to what we say. It's very important. So on this first day, I want to talk to you about the things that are critically components of living things. Because our whole class is about biochemistry. That's the chemistry of living things. You may not be aware, but there was a time when folks thought that the chemistry of living things was different from the chemistry of non-living things in some vitalistic way. We no longer believe that. We think that living things have the same kind of chemistry as other things, but they function in a way that's amazing. So, to do that, I thought we'd start with letting Dr. Francis Crick speak to us. Now, you remember from what I told you before, Crick and Watson were famous for discovering the structure of DNA. Good job, thank you. And he is an expert on the way life functions at the chemical level. So we're going to let him talk. So I'm turning to page 72 of his little book called Life Itself. The subtitle is Its Origin and Nature by Francis Crick, Nobel Prize winner. Life as we know it on Earth. May I interrupt the quote there just a minute? These guys will talk about life as we know it, as if there's any other kind of form of life. May I make it very clear to you, class, there is no other form of life that anybody knows one thing about. Okay? So when we say that, just understand, this is the way life is. They can make up stories about how other kind of life forms might exist, and you've all seen science fiction things with all kinds of weird creatures that look like they're different forms of life. There is no such thing anybody knows anything about. That's thrown in free of charge. Life as we know it on Earth appears as a synthesis of two macromolecular systems. And I've already lost you. Every living thing, class, has two kinds of giant molecules. Every living thing. And he's going to describe those to us. The proteins, because of their versatility and chemical reactivity, do all the work, but are unable to replicate themselves in any simple way. So the first great class of molecules we're going to talk about are proteins. So class, would you please say that? What are we going to talk about first?
Proteins.
Good. That's one of the answers. The nucleic acids, which is the other great class, seem tailor-made for reproduction, but can achieve rather little else compared with the more elaborate and better equipped proteins. So the other class of molecules is the nucleic acids. So say that for me.
Nucleic acids.
Good for you. Those are the two giant molecules that are in every living thing. And they have to be there, or you don't have a living thing. Well, I don't know if I should read this or not. I think I will. If you understand that this is not me talking. Does everybody get that? This is not me talking. The RNA and the DNA, those are the nucleic acids, are the dumb blondes of the biomolecular world. Fit mainly for reproduction with a little help from the proteins, but of little use for much really demanding work. I'm sorry, ladies. I didn't say that, but that's probably the one thing you're going to remember, what I said tonight. Yeah. The problem, says Dr. Crick, of the origin of life. How did life get started? You remember I said to you last night, that's probably the most important question. Would be a great deal easier to approach if there were only one family of macromolecules capable of doing both tasks. But life as we know it employs two. Always. So, I'm going to skip ahead here because I'm afraid I'll forget it later. On page 88, he says this: an honest man, armed with all the knowledge available to us now, could only state that in some sense the origin of life appears at the moment to be almost a miracle. So many are the conditions which would have had to have been satisfied to get it going. And may I say amen to that? Folks, when I get finished, I hope you're going to be stupefied with how complicated this is. And by the way, let me say right here that that professor that I mentioned at Florida College, I wish he were still alive today. Because in the last 60 years, we've learned so much more about the way life functions. And folks, we know less today by light years than we thought we did 60 years ago about how life comes about. I'm telling you, we are lost when it comes to the question, how did the first life get started? And the more we learn, the worse the case gets for those who think it started by itself. Period. So what does this man do with that? He says, if it was highly likely, there's no problem. Are you kidding me? It was highly likely that life just started by itself without anything else. But if it turns out that it was rather unlikely, has to be the understatement of the century, then we are compelled to consider whether it might have arisen in other places in the universe where possibly for one reason or another conditions were more favorable. Are you listening? He said maybe if it didn't have enough time in 4.5 billion years on earth, maybe we got to look somewhere else as to where it originated by itself without God. And you know what the rest of this book's about, class? By this Nobel laureate, it's about directed panspermia. Does that mean anything to you? Panspermia is the doctrine that somebody sent the first living things here on a spaceship. And directed means it was purposely done. Is there one scintilla of evidence that some other civilization sent the first life forms here on a spaceship? No, class. I don't care if anybody talks to you about little green men. There is zero evidence. But this Nobel laureate will take that before he'll take God, which tells me a lot. There's a whole chapter in here about what the spaceship would be like. I'm not kidding. You read it for yourself. Nobel Prize winner Francis Crick. No, class. When I get through with you, what I want you saying is there's no way that came about without a designer who planned it. So what is life like? It's made up of two giant types of molecules. There are the structural materials, which are proteins. And do you see this? They are assembled from amino acids. Class, proteins consist of a string of amino acids. So if I say to you, here's a string of amino acids, you can say that constitutes a protein. Excellent. And they make up the construction or the shape and mobility of living things. Secondly, there are the tools and machinery. We call them enzymes. But class, an enzyme is just a special type of a protein. Yeah. So both of these are proteins. Enzymes are a special type. But they make up the metabolism of living things. That's the growth and maintenance. Proteins. As he said in his book, they do most of the work. But that's not all there is. There's another type we call the blueprints. These are the genes or the nucleic acids, the DNA and the RNA, and they are for reproduction. They contain the information and directive function of living things. The information that guides all this process is found in the nucleic acids. Nucleic acids, folks, do not function without proteins, and vice versa. They need each other. and one generates the other. So that's the basic outline from Francis Crick's book of the living things. And class, if it's a one-celled organism or if it's you and anything in between, you're going to have this. Okay? So can I pause here just a minute and say, do you know what an evolutionist says about that? Why is it that all living things have a common chemistry? They say, because all of us, if we trace our family tree back far enough, no matter what kind of living thing we are, trace back far enough, we all come from the same common source, which was a single cell type organism, or the simplest kind of organism, millions and millions of years ago, and then we evolved into the tree of life by natural causes. We have a common chemistry because we have a common ancestry that evolved into all of us. Folks, that is not a stupid answer. That is a possibility. It's one possible explanation for this fact. What do I do with that fact as a creationist? I say if a creator was trying to design a system that has to interplay with itself and like feed on itself, wouldn't it need a common chemistry? And do you have to start all over every time you do something? No, you can use a common design, especially if you're trying to create something that's to work together in a unified fashion. So that's another perfectly reasonable explanation for our common chemistry. You have to go deeper than that to decide which one of those is the best answer if you're using only science. Maybe now's the time to tell you, if you ask me, do I believe in evolution? My answer is yes and no, like any good politician. It depends on what you mean by that. If you mean things have changed over time, I believe that. Dramatically can be demonstrated. If you mean by that all living things come from a single tree of life, I do not believe that for 1 second, nor does the evidence support it. Some folks call that the general theory of evolution versus the special theory of evolution. I believe in limited change, but not enough change so that we're all kin to one another, from single cells all the way up to elephants. Are you with me? Okay, so don't deny evolution, class. It's hard to argue with facts. Evolution is demonstrable if you mean limited change. All right. Let's talk about how this works now. Class, this is day 1 in biochemistry. I told you every living thing has proteins and nucleic acids. We're going to talk about proteins first. And what you see before you are the 20 common amino acids occurring in proteins in every living thing. So, of course, the first thing you're going to do is memorize these 20. And there will be a quiz tomorrow morning. And when you walk in tomorrow, you're going to write those 20 with their abbreviations. You notice they're 3-letter abbreviations? Let's point out a few of them. GLY is glycine. Notice it's relatively simple. And way over here, histidine, HIS, is a little more complicated. And there's several of them. Tryptophan's pretty complicated. But you see, most of them, it's the first 3 letters, isn't it? This one, IU, is not quite that way. That's isoleucine. Here's threonine, that's THR, and so on. But there's 20 of them. If you take a protein, if I take a cell out of your body and I analyze the protein in it, it's going to be made of those. Forgive me, if I take a cell out of a little salamander, it's also going to have the same thing. Sorry. That one's chemistry is the same as yours. That's the truth, class. You can go to the lab and do it yourself. They're made of these 20. Well, that's interesting, isn't it? Every protein in every living thing is made of these. That means if you eat a salamander, you can use his chemistry. I don't eat salamanders too much. Every protein is a combination of those 20. It's very much like the 26 letters of the alphabet in English. Every word in English is constituted by a combination of 26 letters. Right? Even anti-disestablishmentarianism is still a combination of those 26 letters. And by the way, anti-disestablishmentarianism is a long word in English. The average protein is way longer than that. Did you hear me? An average protein may have 1,000 of these in a row. It's a way bigger word in protein language. But it consists of a combination of those 20. And by the way, another point should be made here. When you're making letters combined in English, only certain combinations mean something, isn't that right? I mean, you can have gibberish. The same is true with protein language. There's lots of combinations of amino acids that don't work. They're not proteins. They don't work. So you have to have the right combinations. Now, there's lots of right combinations, but there's a whole lot that aren't right. And if you don't have the right ones, you got no protein functioning. Okay. So what are we doing on our first test tomorrow? You're going to name me the 20 amino acids and their abbreviations. Good. Now let me go back one more time here and tell you why they're called amino acids. You'll notice there's an NH3 group right there. There's one here, 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 and if you look, can you see one in every one of those? There's one, there's one. They all have an NH3 group. That's called an amine. So it's an amino, and it's also called an acid. And you see that little COO group right there? That's a carbon and 2 oxygens with a negative charge on the side of it because one H has been removed. It's an H ion, which makes an acid in a solution. So when you can remove an H ion and make it an acid solution, it's called an acid. So those are all called they're called amino acids. Every one of them has an amine group and an acid group. See, there's the COO there. That's question number 2, class. Okay. I think you're still with me. Good. Let's talk about the other giant molecules. They're called nucleic acids. And may I offer my apology to all proteins for not spending the next 6 weeks with that? That's what we ought to do, because proteins deserve a lot more attention. But we must go on. So DNA, notice the structure here. There's a strand and then another strand wrapping around it, and you see there's cross pieces. So it's known for its double helix with crossbars. That's what Crick and Watson discovered. And by the way, can I throw this in free of charge also? Crick and Watson get all the credit, but did you know most of the work was already done by the time they got to it? As is typical in science, the one that gets the credit and all the glory is the guy that puts the icing on the cake, generally speaking. Just understand, there were lots of dedicated chemists that worked on this problem for a long time, and Francis and Crick got the Nobel Prize. Francis Crick and Watson, yeah. Which is just the way it is. Sorry. But they did discover the double helix with crossbars, and because of that, it has the capacity to reproduce itself. And what they discovered over time was that these cross pieces consist of exactly 4 different kinds of bases, they call them. On this picture, there are blue ones and green ones, yellow ones and red ones. That's not the way it is, class. They're not colored that way. But they are done that way in this diagram so you won't forget it. And what you'll find out when you study this is that it's always, notice, the red always hooks up with the yellow. You see that? And the green always hooks up with the blue. So down here, it's the A and the T that always join together, and the G and the C joined together like love and marriage and a horse and carriage. Some of you are starting to fall asleep on me. I'm watching. Here is what we've learned. This was discovered in the 50s and the 60s. By the 70s, we had learned that there was a genetic code inside the DNA. We learned how to read it. You're going to learn how to read it. And the next quiz next week will be on this. So I need to take a minute here and teach you how to read. This is a language that has only 4 letters in it, G, A, C, and T. And by the way, in RNA, that T becomes a U. It's called uracil, and don't ask me about that. It's a good question, though. All right, so there's 4 letters. If this is the first letter, and that's the second letter, and that's the third letter, you can make every word in this language because every word is 3 letters. So let's practice. What if the first letter is T, the second letter is T, and the third letter is T? That's the word T-T-T. It is pronounced t-t-t. This is not a spoken language, ladies and gentlemen. But it does have meaning. What does T-T-T mean? Well, I will tell you, it means P-H-E. Well, that's easy enough. Doesn't help much, does it? Unless you were alert and you already did what I told you to memorize. PHE is one of those abbreviations for the amino acids. That stands for phenylalanine, one of those 20. So the letters TTT in a word stand for phenylalanine. Folks, this took some time to figure out, can you imagine? But over the next 10 or so years after the 50s, they had figured out the genetic code. Amazing accomplishment. Let's try another one. How about A-C-T, ACT? That means threonine. By the way, do you see some repeats up here? TTA, TTG, CTT, CTC, and CTA, and CTG are all leucine. There are 64 words in this language. There are 20 amino acids, so you have repeats. Looks like a backup plan to me. In addition to all those amino acids, there's something else. Can you see something different up there anywhere? It doesn't look like a 3-letter abbreviation. I'm giving you a hint. What do you see? Yeah, right here. Term. That stands for terminator. What do you think it means? Anybody want to take a guess? It means that's where you stop reading. That's the end of the strand, yeah. Terminator. That signal means you have finished the strand of amino acids. And a strand of amino acids is a protein. That was very weak, class. Did you hear what I said? A strand of amino acids is a protein. Exactly. And how do you know when it starts and stops? There's a signal for that. Terminator. And there are 3 signals for terminator. Let's go back. 3 signals for terminator. TAA, TGA, and THE. But if you're reading along and you come to TAG, that means stop reading. That's the end of your chain. Now, not shown up here, there's also a start reading signal. And it's right here, methionine. This ATG is a start reading signal. So you've got a signal that says start reading, read 3-letter words, and stop reading. In between you have a sequence of 3-letter words, each of which stands for an amino acid. So you have a string of amino acids, which is a protein. Exactly. I've just taught you how to read. And in every cell of every living thing, that code exists. Every living being has a code in it like that. And it's the same code. I don't know how you feel about that, but that is incredible to me. If you were a jury, and I was going to try to convince you, jury, that somebody did this, It didn't happen by natural causes. I would say to you, give me one single example from all the history of mankind where a language came about by natural causes. Just came about. There is none, in case you're worried. Language is always produced by an intelligent source. There is no exception to that. So every living thing has a language in it. That says to me, ladies and gentlemen of the jury, this was built by somebody. I call him God. That's the most reasonable explanation for the existence of a language in every living thing, not that it had some natural cause over millions of years. You believe it or not, that's your call. So all 20 amino acids here, along with a terminator and a begin reading code. But there's so much more to this story, class, because we knew all of that by the 1970s. What I'm about to talk to you about now was not well understood until later on. And since then, we've learned a whole lot more that I'm not even going to talk to you about. But here's the problem. The DNA, for the most part, exists in the nucleus of eukaryotic cells. And it contains the information which you can then use to build proteins. And therefore, it's the guide for life. But it's up here in the nucleus. Down here in the cytoplasm is where all the action's taking place. So you have to transcribe the information off of the DNA. Then it has to migrate outside that nucleus, and it has to be picked up out here by two ducks hugging each other. Isn't that what that looks like? That is not what it looks like, class. But they draw it that way to make it interesting. Those are called ribosomes. And the information then has to be translated in order for the protein to be built. See the protein coming out the bottom here? So the information comes from up here, it's copied, migrates, is read and translated, and then a protein is built. And boy, is that an oversimplification. There are so many things happening right there, class. We won't have the time in the next 2 semesters to talk about all that. So I have a few minutes to try to get you stupefied. So don't you lose me. Let's blow this up a little bit. The transcription part of this. Here's the DNA molecule. The information is in there, but you can't copy it unless you unzip it. So class, the answer to my questions for the next several minutes is protein. You got it? What do you think it takes, class, to make the DNA unzip?
Protein.
Thank you very much. That's right. It takes more than one protein. Do you notice that over here it's zipped back up? It's zipped back up again? Have you ever had trouble zipping things up? Do you know that DNA can get tangled up also if it's not careful? Because it's an extremely complex thing. Did you know there's a specific protein to help it zip back up? There is. All right, let me ask you to do this, class. As we're going through this next few steps, would you kind of keep track of how many times I ask you to say proteins? And may I say to you, every time I ask you to say it, there's usually more than one involved. And certainly in this first step up here, to unzip it and cause this process to happen, there's several proteins. All right, so now you're making the copy. That's the messenger RNA. As you make that copy, class, what do you think it takes to make the copy?
Protein.
Exactly right. Remember, we're in the process of building one protein. You listening? I'm showing you how to build one protein. And already I've told you it takes several proteins to build one protein. Okay? Let's keep going. Now, once it's built, we're going to focus in on the messenger RNA over here. You also have ribosomal RNA and transfer RNA. We're not talking about that. That's another whole 2 or 3 weeks. We're over here. The messenger RNA has to be matured after it's copied. You see those little white pieces? Those are called introns. We didn't know much about those till the 80s and 90s. And what we learned is the body here, your cells, snip those out. They are edited out by, what do you think, class? Proteins. The things that edit them out are called editosomes. They are enzymes, but an enzyme is a special case of a protein. Exactly right. So there's some more proteins involved in the editing process of messenger RNA. And they restructure it, and once you snip that out, don't you think you got to put it back together? That's called splicing. And they're very specific to splice it back together. They're called spliceosomes. And folks, in the last several weeks, I have spent hours studying spliceosomes. Can I explain to you briefly? A spliceosome is a combination of several different proteins and other things that works together in a complex structure. It's incredible how much is involved in just splicing that back together. Pardon me if I yell so much. But I can't believe that intelligent people sit around reading, writing, and talking about how this came about by natural causes. There's no way on God's earth. So yes, a lot of proteins involved right here in an extremely complex process of maturing the messenger RNA. And may I take another little side trip? You know what the evolutionists started saying early on when we discovered about those introns? They said, well, that sure looks foolish. Why would some God make it so when you made the copy, you had to mature it? Why don't you just make it so when you copy it, you can use it? Looks like an evolutionary process that's left over from your evolutionary past. And by the way, those introns, they're just junk that are thrown away. They're not even used for anything. They're junk DNA. So from the 90s to the 2000s and really on up into 2010s, many scientists were writing books about junk DNA and saying to you, if you're a student, DNA is supposed to be a grand testimony for a creator. It's the terrible testimony because it's full of junk. You really believe God made a bunch of junk? That's exactly what was taught and written about. The problem with that is, I have a new little book here called The Myth of Junk DNA, because it is a myth. That didn't keep a lot of Nobel Prize scientists from calling it junk. And I say, be careful what you call junk. Maybe you should be humble enough to say, I don't know what's going on here. Let's wait 20 years. Because I'll tell you what we found out. Those introns are doing all kinds of things we knew nothing about 20 years ago, including making little messenger RNAs and a bunch of other stuff. Read the book. But that's not what the evolutionists were saying, because they want to get you to believe this is a result of a natural process. That's a bunch of junk there, and that's evidence of non-design. Now you got to migrate outside the nucleus. Ladies and gentlemen, every nuclear membrane has holes in it. Do you think any respectable nuclear membrane is just going to let anything go through those holes? No, it is not. So what do you think, class, guards the hole and only lets certain things through, like messenger RNA? Proteins. Pretty good. You were hesitant. When the messenger RNA comes up to that hole, it says, here I am, and this protein just opens up and says, come on through. and then closes back up. It's a specific protein involved with migration. And you said it, right? All right? Then we're outside. Here comes the messenger RNA outside that hole. By the way, the ribosomal RNA and the transfer RNA have to do the same thing. Involved in all of that. I mean, there's proteins everywhere involved. So it comes out here and it's picked up by these two ducts, the ribosome, and it reads the information. See the three-letter words here? That's information that came from the DNA up there and is being read. And as it's read, it calls for transfer RNAs that bring in the specific amino acid for that three-letter code and brings it up here. And what do you think, class? Every one of those transfer RNAs is exactly the right one for that amino acid. There's 20 of them. And for each one of them, there is a specific protein. Exactly right. That's 20 more proteins that allow that function to take place, to bring the amino acids up here to the ribosomes and allow it then to build the protein. When you get inside here, there's more, what do you think? Proteins involved in making the process happen inside here. And then we're going to show you something else here in a minute. There's more. In this very first step, when the DNA unzips, it requires a glob of about 9 proteins to make that happen. If you don't have those, you get no information off the DNA. The proteins that are required right here in that step also have to be built by this same process. Did you hear what I just said? So one of them is ribonuclease. That's another enzyme. Ribonuclease has to be built this way. So how'd you get the first ribonuclease? Looks like a plan to me. They had to be present. You had to have ribonuclease to build ribonuclease. And all the other proteins that are in the process, there's at least 50 different proteins involved in making one protein. Every one of those 50 had to be built by this same process. But if the things that were needed were not there, you don't ever get them. That's why Crick would say it would be a lot easier if there was only one giant family of molecules to do both jobs, but it never happens that way. It's always two. And they always interplay with one another, and you have to have it all. And there's not a human being on earth that can demonstrate otherwise. But they will tell you in their textbooks, this speaks to a natural cause over millions of years. It does not speak to that. It speaks to an intelligent designer who put this together instantaneously. Or it wouldn't work. I want to introduce you to Drew Berry. He's called a biomedical animator. He takes minuscule things and makes pictures out of them, makes it come alive. They're so small you can't see them. Naked eyes, and most of our microscopes will not handle that either. So he makes an animation for you. And so he does that for biomedical topics. He's at the Walter and Eliza Hall Institute of Medical Research in Australia. He has a website. If you want to have some fun, kids and mamas and daddies, go to his website because he's got lots of videos. I'm going to show you one tonight and 2 tomorrow night. 1 tomorrow night from him. So I highly recommend him. So here we go. You see up there in the left-hand corner, this is a Drew Berry video animation of building a protein. Mr. Eric, are you alive and well?
I'm here.
Yes, proteins are chugging away back there. Class, if you weren't here before, I must tell you, Eric is my AV guy. He's done a lot of work to make this thing happen because you can't teach this material without visuals. And I'm now putting him to the supreme test. Because we're going to make this a video, and I'm the moderator. There's a moderation behind here, and it's in British English. It's pretty neat, but I don't like it because it's evolutionary. I'm going to be the moderator. And he is going to start and stop at my command. And he's going to do it instantaneously, and if he messes up, it only ruins my whole speech. So there's absolutely no pressure on Eric. No, we're going to work together. But he's done a lot of work on this and gotten ready. So I appreciate that very much. So let's go just a little bit forward, Eric. Stop right there. Do you see this says, this is the start of a gene for a bone strength protein. We're going to build, class, on this video, a bone strength protein. That's our job. And he's going to show you in live Technicolor how that happens. So first let's notice here, this is the DNA strand. You can see how it's wrapped around itself. And the information is inside of there. And this glob right here is a glob of, what do you think, protein? A class? Oh my. What do you think, class? Protein. That's good. Now, there's a red one, which is not red. There's a blue one, which is also not blue. And there's a lighter blue and a green. So there's 1, 2, 3, 4, and there's another one hiding back in there you can't see. So there's 5 already in that glob, right? He colors them so you can identify that there's different substances. All right, let's go on a little bit, Eric. Okay, you watch. This is down inside the nucleus. There, stop right there. See the little vitamin D here floating in its cytoplasm inside the nucleus? That vitamin D is critically important because the vitamin D is going to activate this bunch of proteins here, as you will see in the picture. Understand that some of this isn't real like it really happens, but it gives you the picture. So here we go. Keep going. Here comes the vitamin D. Stop. And the red protein turns green, which of course it doesn't. Green means go. That's why he does that. Red means stop. So the vitamin D class makes the whole process get started to build this protein. So get your vitamin D class, get outside your house sometime, off from behind your computer, and walk in the sun. It gives you vitamin D naturally. That's thrown in free of charge. Let's keep going. The protein now has been activated and stuff starts happening. Here comes another glob of what, class? Protein. More protein. Stop right there. There's one. See the little dark one back in behind there? That's 2 more proteins that have just joined this glob of proteins riding along the DNA strand. Keep going now. As this transcription stops, stop right there. This is called ribonuclease. It separates and starts riding along the DNA molecule, and then it opens it, and you're going to see in a minute what happens. Let's keep going. It finds the right spot, of course, because you've got to be in the right place in the DNA. And it's stopped right there just a second. The DNA strand is here. Here's the glob of protein, and the transcription is taking place down inside there. And this messenger RNA, you see this orange thing? That's the messenger RNA. It's being built down in here and released out into the cytoplasm while this is all taking place. So far, so good? Let's keep going. What we're going to do now is going to magnify this and look inside here. Stop right there just a second. See all these little things floating around here? That's all materials that have to go inside that protein glob to be used to build the messenger RNA. They're critically important. And there's a bunch of other stuff happening we're not talking about. Please understand, I'll be on my knees tonight by my bed asking God's forgiveness and the forgiveness of every protein and DNA for the pitiful job I've done. Because every step of this so far, I've left out 16 things that are going on at the same time. Please understand, there's almost so much detail a body can stand. But what I'm showing you right now is happening in every cell in your body while you sit there. You wonder why you get tired sitting there listening to me? you've got 30 trillion cells that are very busy. So let's keep going. We're looking down inside here now, and see how it's unzipped? Stop right there just a second. The DNA is unzipped, and you see the code exposed down there. There are not little T's and G's written on this, class. That's there to show you there's the code. 3-letter word, 3-letter word, 3-letter word. And each code is being matched. If you have an A over here, you're going to have a U over there on the messenger RNA. If you have a T over here, you're going to have an A over there. If it's a G over here, you're going to have a C over there. If it's a C over here, there'll be a G over there. The exact mirror image is being made. What I want you to notice, class, is when that unzips, which requires what? A glob of proteins, it opens up and every one of these letters is copied. So let's do a little math. A typical protein is 1,000 amino acids long. Each amino acid has a 3-letter code. That's 3,000 letters, right? That have to be copied. Each one is copied independently. And when you get them all finished and you read the stop code, you're done. And the messenger RNA is released. One of the challenges for videos that I have used over the last 10 years is that none of them could show you how rapidly this really happens. So one of Drew Barry's ideas on this one was to show you live how fast this takes place. So that's what we're going to see next. Watch. Go. That's way too slow, class. Way too slow. Come on. That's more like it. Stop. You see that, class? A protein whose code is in the DNA that's thousands of amino acids long can be transcribed in microseconds. And your body builds thousands of them every minute. Just watch. Go. And now it's going to be released. There it comes. Stop. The one thing I don't like about this Drew Barry video is he doesn't show the migration from the nucleus, from the DNA out to the nuclear hole. He doesn't show those proteins opening up. But they're there. And on this side of that hole, what do you think's on this side to guard that side of the hole? Another protein. And so it's now come through the hole and it's migrated out into the cytoplasm of the cell itself. And that's your messenger RNA with the message on it containing the information that was copied up here by the DNA. And we've already used about 25 different proteins so far. Let's go. Here comes the 2 ducks. But it doesn't look like 2 ducks, does it? That's the RNA that comes up. That's the ribosome that comes up. And now, whoops, I messed you up. That was my fault. Can you get me back to where we were? Did you see how he did that? That's a miracle. I hit the wrong button up here and we went back to the beginning. So he recovered me. All right, so here is the ribosome. Here is the messenger RNA being read through it. And you see these little guys coming up here? Those are transfer RNAs. Now we're getting a little blow up of that. These are transfer RNAs, and you see the little red thing on the end of them? That's coming back up here in just a minute. And Eric, get ready, because I'm going to have you stop in just a second here. There, now. That's a transfer RNA. It looks a little bit like a seahorse to me. But it's a chemical made out of, what do you think, class? Protein and some other materials. And on the end, it carries the amino acid specific for that transfer RNA. There's only 20 of them. There's specific ones just for that. So let's watch here a minute, because it's going to show us different ones. Watch. There's a different one, different one, different one, different one, different one. That's it. So there's one for each one. And it comes up here as the code is being read. We're going to go down inside here and look a little closer. Stop right there just a second. Can you see the code here? There's a three-letter, 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 three-letter. And it's reading the code. It's calling for the specific transfer RNA who has the code matching it right there on its end. And up at this end, it's carrying the amino acid that goes with that code, which amino acid will be added to this string of amino acid, which makes a protein. Right. Let's watch a while. Stop right there. Class, every time this transfer RNA does its job, it is dismissed, goes back into the cytoplasm, and is recycled. Done its job. Then it goes on to the next one. Keep going. This is way too slow. Shape up. All right, he's going to try to show you. But he's miserably failing. You see the protein coming out the top there? This is hemoglobin that's being constructed. And now you're going to watch it one piece at a time. You know why it stops, because it's come to the terminator, and it stops adding to the protein. And when it gets to the terminator, releases the protein into the cytoplasm. Boom. Stop right there. That's a precise string of amino acids, which makes a... No, you're right about that. But that's not all there is to it. It's not enough just to have the string of amino acids. That protein has to fold up on itself in a specific two-dimensional structure and three-dimensional structure. And it's not finished even when it gets here, because it has to migrate into another organelle where other... I know you're getting tired. Inside of another organelle, there's another protein that helps shape that into its final condition, and until that happens, class, it does not work. You want to read an interesting book? You read an interesting book by Douglas Axe, who did lots of study on this and showed that only certain structures for that DNA, no matter what the strand is, only certain structures work. And it's minuscule. Most of them don't work. Look, if you don't fold that thing up just right, it doesn't work, class, and it's useless. Looks like a design to me. So this thing goes through another stage using more proteins until it's finally released into the cytoplasm. And this is what biochemistry books will tell you when you read your book. Here's what it's going to say. It releases the protein into the cytoplasm to do the job for which it was designed. And then they proceed to tell you, but it wasn't designed. And I say, the chemistry of building proteins in every living cell is sufficient to proclaim there must be a grand designer. That is the most reasonable answer. But we have learned so much more about the chemistry of living things in the last 50 years. I haven't touched the veritable hem of the garment, class. Because look at this. That's a picture of a modern day cell as we understand it. We call it a self-replicating nanoscale robot. Why do we do that? It's self-replicating because it can and does reproduce itself. Did you know every cell in your body can reproduce itself entirely? Come back tomorrow night and I'll show you. And in the process of doing that, your cell uses machines that we knew nothing about 30 years ago, thousands of them, to do the work, to do the reproduction. It is a process the likes of which, we didn't touch it, class. 20 years ago. But it copies itself. It's self-reproducing. Secondly, it's nanoscale because it's at the very small level. I told them last night a nanometer is 1/1000th of a meter. That's pretty tiny, wouldn't you say? That's the level we're talking about here. And at that level is what this does. And then it's a robot because its activities are carried out unconsciously and automatically by precision molecular machines that follow ordinary physical laws. And nobody argues with that anymore. These are all things we've discovered in the last 75 years. Is it any wonder that philosopher, atheist, author, and debater Anthony Flew, when he turned 80, after having spent his whole life speaking, writing, and debating against creationists and calling us foolish and speaking out against us, though he never was as ugly as Richard Dawkins. He's not a mean person. And he always said, I have taken the position since I was 15 years old and became an atheist. I will follow the evidence where it leads. And so at 80 years old, he wrote this book. There is no, a God. How the world's most notorious atheist changed his mind. I just turned 80, class, so this means a lot to me. I hope I'm still open-minded enough to change my mind about something if the evidence is abundantly clear. And if you're listening to this lecture and you're an atheist, will you please at least listen? Richard Dawkins speaks passionately a lot, so I make no apology for yelling and emphasizing points. I want them driven into your mind so hard you can't forget it. Let's listen to what Dr. Flew said. It has become inordinately difficult even to begin to think about constructing a naturalistic theory of the evolution of that first reproducing organism. The enormous complexity by which the results were achieved looks to me like the work of intelligence. It now seems to me that the findings of more than 50 years of DNA research have provided materials for a new and enormously powerful argument to design. And he's honest enough to admit that. Not only that, he's honest enough to publish a book that he's completely changed his mind. Now, he doesn't believe in the Bible's word of the God. He doesn't believe the Bible's the word of God, but he believes in God. There has to be. And how did he get there? Strictly from the evidence of the scientific world. And so can you. The evidence is overwhelming, class. You were designed, and everywhere you look, from the macroscopic to the microscopic, the evidence is overwhelming. Don't ignore it. And once you come to believe that there's a God, then may I request of you that the next step you take is become convinced this is God's word to tell you how to live. That's where you go next. Because in John 14 in this book, Jesus the Christ said, you believe in God, believe in me also. That's where you need to go next. Thank you for your careful attention. You get an A for attention, class. I didn't even have to make you stand up tonight. That's remarkable. Because this is not easy material. And you hung in there. And most of you were pretty alert. Thank you for your attention, and I'm done. So whoever's taking over, please do so.